Hello. In the next series of videos, I want us to discuss DC motors. I've divided the series into various topics, and the first topic is actually a combination of two topics. I want us to talk about the purpose and applications of DC motors, and then we look at the equivalent circuit and operating a DC machine as a DC motor. Just as with any other type of rotating machine, the DC machine can operate either as a motor or a generator. However, applications requiring the operation of the DC machine as a generator are limited, while applications requiring the DC machine to operate as a motor are commonplace. DC motors transform electrical energy into mechanical energy, and DC generators do the reverse. DC motors are the obvious choice in applications where DC sources are all that is available. For example, in automotive systems. One capability that DC motors possess that induction and synchronous motors do not is precise speed and torque control. Many industrial applications require motors with a high degree of flexibility in the control of speed and torque, making the DC machine the motor of choice in that area. DC motors have a broad range of speed control capabilities coupled with a high efficiency over the range and can be built with torque speed characteristics to suit any particular application for both DC motor and regeneration applications in either direction of rotation. Continuous operation of DC motors is commonly available over a speed range of 8 to 1. Infinite range, that is smooth control down to 0 speed for short durations or reduced load is also common. DC motors are often applied where they momentarily deliver 3 or more times their rated torque. In emergency situations, DC motors can supply over 5 times their rated torque without stalling or stopping. Dynamic braking, that is DC motor generator energy, is fed to a resistor grid, or regenerative braking, that is DC motor generated energy is fed back into the DC motor supply, can be obtained with DC motors on applications requiring quick stops, thus eliminating the need for or reducing the size of a mechanical brake. So braking, which is known as electrical braking, which is easier to apply, is easy also to achieve in a DC motor. DC motors feature a speed which can be controlled smoothly down to 0, immediately followed by acceleration in the opposite direction without power circuit switching. DC motors respond quickly to changes in control signals due to the DC motor's high ratio of torque to inertia. DC motors are widely used in electric traction on railways where their drooping torque speed characteristics and a wide range of speed control capabilities are valuable. Other applications include cranes and other hoisting equipment. Large DC motors, that is in the range of 12 megawatts or so, are used as drives in blooming and slabbing mills and as propulsion units in diesel-electric ships. In most cars, tractors, and aircraft using the DC electric supply, all auxiliaries are driven by DC motors. Small DC motors in the range of tens of watts are employed in various automotive control applications. The direct current needed to drive these motors is supplied by DC generators or AC to DC converters or rectifiers. In summary, the most important characteristics of DC motors include adjustable motor speed over wide ranges, constant mechanical output or torque, rapid acceleration or deceleration, and responsiveness to feedback signals. Now, let's look at a DC machine operating as a motor. Since we have already covered DC generators, I'll keep on referring to what you know, the DC generator. Now, there's a difference of construction between a DC, There's no difference of construction between a DC motor and a DC generator. The only difference is that in a motor, the generated EMF is less than the terminal voltage, whereas in a generator, the generated EMF is greater than the terminal voltage. Therefore, in a generator, the current and the generated voltage are in the same direction, whereas in a motor, the two are in opposite directions. If E is the EMF generated in the armature, V is the terminal voltage, Ra is the resistance of the armature, and Ia the armature current, then when the DC machine is operating as a motor, the EMF E is less than the applied voltage V, and the direction of the current Ia is the reverse of that when the machine is acting as a generator. Hence, the EMF equation will be as follows. E, which is the generated voltage, is equal to V minus Ia Ra, where Ia is the armature current, Ra is the armature resistance of the windings, and V is the supply voltage. Or in terms of the supply voltage as being the subject of the formula, V is equal to E plus Ia Ra. So let's call this equation 2.1 for reference. Now later we'll talk about E and also we'll talk about Ra. Now the motor generated voltage E is known as the back EMF. Therefore, in the motor armature, the effect of the applied voltage V is reduced by the influence of the back EMF, which is established through the process of electromagnetic induction in opposition to the applied voltage. This simply means that whilst a force is being created on a conductor to produce motor action, the same conductor is moving through a magnetic field and therefore has a voltage or an EMF induced in it. Thus, whilst the machine is being driven as a motor, part of it is still working as a generator, that is, inducing an EMF. The underlying principle is Faraday's law of electromagnetic induction. This is what we can see in equation 2.1. There is a generated voltage and there is a supplied voltage. The supplied voltage is V, the generated voltage is E, and that's the one we refer to as the counter EMF. It opposes V. It is also known as the back EMF, as I've mentioned already. Now, the back EMF or the counter EMF E is only present when the motor armature is turning. By Faraday's law, there must be motion. If the motor is stopped, then there is no induced EMF. So no lines of flux are being cut, and the armature current will be a maximum. So we can refer to this as a short circuit, as V is equal to IA times RA. Now, the induced EMF can never be equal to or higher than the applied voltage. This is motor action. It only happens in generator action. The equivalent circuit diagram of the DC machine as a motor is based on equation 2.1, as we shall see later. RA may be taken to include the interpole winding resistance, the compensating winding resistance, or alternatively, they may be taken separately, connected in series with the armature resistance. The brush resistances may be taken separately, if quite substantial, or they may be lumped in the armature resistance. An alternative is to look at the effect of the brushes in terms of the voltage drop across the brushes and not in terms of the resistance. Either way, we come to the same thing. Now let's look at the equivalent circuit of a motor. But let's first assume negligible brush resistance, and let's omit the interpole and compensating winding resistances. Then our equivalent circuit diagram of the DC motor, the DC machine operating as a DC motor is as shown in figure 8.1. Let's call it figure 2.1. So see this in figure 2.1. So this is the equivalent circuit diagram of a DC machine operating as a DC motor. So let me include that one. Operating as a DC motor. So let's look at it closely. We have the armature, which is represented by a circle, and M means it's a motor. Then you have the brushes. Those two black rectangles represent the brushes. We have the armature resistance, which is the resistance of the armature windings. And then we supply the motor with a voltage V, which is a DC voltage. When the current flows, which let's call it IA, there's going to be a voltage drop across the armature winding resistance, IA times RA. Now, the motor needs to be excited, so there's a field winding. And once the motor is running, there's also a counter EMF, E, which is a generated voltage in the motor. The counter EMF, also known as the back EMF, opposes the supply voltage V. So we can say it controls how much current goes into the motor. In section 3, I want us to talk about the classification of DC machines. And those machines are DC motors. So let's change this to DC motors. Once again, as we saw, okay, beautiful. Once again, as we saw when we're discussing DC generators, we saw that the behavior of DC generators depended on the manner in which their field windings were connected to the DC excitation source. So the same thing applies to the motors. That is, the behavior of DC motors depends on the manner in which their field windings are connected to the DC excitation source. This may also be used to classify DC motors the same way we saw in DC generators. So as we shall see in figure 3.1, we have got two general possibilities. Figure 3.1 shows the methods of excitation for DC motors. This is now motors. And this gives us two possibilities. Figure 3.1a shows the separately excited DC motor. So once again, we are looking at the two possibilities. Figure 3.1a shows the separately excited DC motor. In this motor, the field winding is provided from a separate supply, an external DC source, which is not the same as the one connected to the armature winding. Now, once again, as we saw in generators, we may want to control the field current so that we control the flux. In a DC motor, we want to control the flux so that we can change the speed. In a generator, we wanted to change the generated voltage. So to do that, we have a field rheostat, which is simply a variable resistor connected in series with a field winding. The second category is that of a self-excited DC motor. This is what we can see in figures 3.1b, c, d1, and d2. In figure 3.1b rather, we have the self-excited, meaning that the excitation or the field current is coming from the same source to which the armature is connected. That is a self-excited shunt wound DC motor. So once again, we see that the field winding is connected in parallel with the armature winding. Together they are connected to the same supply. Once again, we want to control the field current by using a field rheostat. In figure 3.1c, we have the self-excited series wound DC motor. In this one, this field winding, which is known as a series field winding, is connected in series with the armature winding. And then together they are connected to the DC supply. If we want to control the flux, the best we can do in this case is to connect a resistor across the field winding, which we refer to as a diverter resistor, because it diverts some current from the field winding. That way we can change the flux. In figure 3.1d1 and d2, we have the compound. That is the self-excited compound wound DC motor. Now, in this motor, we see that there are two field windings. Essentially, the field winding is connected across the supply. That is the shunt field winding. And the series winding is connected in series with the supply. Now, there are two variations as we saw in the DC generator. We have the short shunt motor, in which the field winding is first connected in parallel with the armature winding, and then the two, or the combination, is connected in series with the series field winding. And and that goes to the supply. Once again, want to control the field, the shunt field current by using a field rheostat. That is the short shunt. So to remember the short shunt, we simply say the shunt field winding is connected in parallel with the armature winding together, or the combination is then connected in series with the series field winding. In figure 3.1D2, we have the long shunt motor. So let's see what this means. First, the armature winding is connected in series with a series field winding. Then the combination is connected in parallel with a shunt field winding. And once again, to control the current in the shunt field winding, we have a field rheostat connected in series. To control for both the flux in the series field winding, we normally connect a diverter or a resistor that is variable in parallel with the series field winding. So this gives us the two classifications: separately excited DC motor and self-excited DC motor. Under the self-excited DC motor, we've got the four variations. Essentially, you can say two variations. That is the self-excited shunt, self-excited series, and self-excited compound. Though in the compound or under the compound, we have two variations. That is the short shunt and the long shunt. Another way of obtaining the magnetic field that is required is to use permanent magnets. Now, because permanent magnets provide the field separately without interfering with the supply, we also refer to that as a separately excited DC motor. So in place of the field winding, we would simply have permanent magnets, North Pole, South Pole. Okay, to conclude our discussion of the first part of DC motors, let's look at two typical exam exercises. A 6-pole separately excited DC motor has a wave-connected armature with 87 slots, each containing 6 conductors. The flux per pole is 20 milliwebers, and the armature has a resistance of 0.13 ohm. A. Calculate the speed when the motor is running off a 200-volt supply and taking an armature current of 80 amperes. And then B. First, derive the torque equation and then use the derived equation to calculate the torque in Newton meters developed by the armature. Note well, NB, for any equation used in your calculations, but which equation is not given in the question, define all the symbols used in the equation. Well, because this was an exam question, so you needed to define those. The first thing is to draw the equivalent circuit. This is a separately excited DC motor. So we have the armature, and then we have the armature resistance, and this motor is connected to the supply. The generated voltage when the motor is running. But before we talk about that, let's talk about the field winding. The field winding has got its own supply. Let's call it VF. And the coil represents the shunt field winding or the separately excited field winding. Then we have a field rheostat which is connected in series with the field winding. Now this motor is running at a certain speed, let's call it NR. Our circuit is a very simple circuit, it's just the armature where a counter EMF or an EMF of self-induction, an EMF due to Faraday's law is induced, EC. This is connected in series with the armature resistance represented by resistor RA. The current from the supply is the armature current, let's call it IA. Now, let's get the motor speed. Step number 1. Number of conductors on the armature, let's call it Z as usual, is equal to number of slots on the armature times number of conductors per slot. Now, in the question, we are given that there are 87 slots and each is containing 6 conductors. So the number of conductors, the total number of conductors on the armature is equal to the number of slots times the number of conductors per slot, which is 87 times 6 is equal to 522. So there were 2 marks, 1 mark for the equation, the other mark for the answer. And then 2, let's find the counter EMF from the equivalent circuit. If we take Kirchhoff's voltage law around this loop, we see that Vs is equal to the voltage drop across the armature, IARA plus EC. So we can find EC. Therefore, EC is equal to Vs, the supply voltage, minus the armature resistance drop, voltage drop, IARA. And this is 240 volts minus the armature resistance current, the armature current rather, is 80 amperes. So it's 80 times the armature resistance, 0.13 ohm. So this gives us 240 minus 10.4, which gives us 229.6 volts. So this is the counter EMF, the voltage generated in the motor. And we can see it's clearly less than the supply voltage. 2 marks once again, 1 mark for the formula, the other mark for the calculation and the answer. Now, the counter EMF of a motor is the generated voltage in the motor. Therefore, we can use the formula of the generated voltage in a generator. Only that this time we are calling it EC. EC is equal to 2 times Z, the number of conductors on the armature, times N, the speed of the armature in revolutions per second, times P, the number of pole pairs, times phi, the useful flux per pole, divided by C, the number of parallel paths in the armature. Now, from this we can make N the subject of the formula. So N is equal to EC times C divided by 2 times Z times P times phi. So all these quantities are given and we have calculated EC. So that is 229.6 times 2 divided by 2 times 522, the number of conductors, times the number of poles was given as 6, a 6-pole separately excited DC motor. So that is P is 3. The flux and the flux per pole is 20 milliwebers. So that will give us the speed in revolutions per second, 7.331 RPS. Multiply this by 60 to change it to revolutions per minute. So 7.331 times 60 is equal to 439.85 RPM. So once again, 2 marks, 1 mark for the formula and the reasoning there, the other mark for the calculation and the answer. That was the first part, the speed of the motor. Now we need the motor torque. First, we are required to make a derivation. do a derivation here. Now, the power developed at the armature is equal to EC times IA. This power comes from the mechanical side. On the mechanical side, we have NR, the speed, and the torque. So the mechanical power minus, of course, the losses. Let's assume there are no losses. The mechanical power is equal to the electrical power. So that's our starting point. So step number 1, the electrical power developed at the motor armature is PD, which is equal to EC times IA. The counter EMF times the armature current. But we know EC is 2ZNP phi divided by C. Then multiply this times IA. Let's call that equation Q 3.1. I'm going to change this one to 1.1. So 1 mark for that. And then 2. Okay, step number 2. The electrical power developed is converted into mechanical power at the shaft, and this power is given as PD is equal to tau D times omega R. So the mechanical developed power is equal to the electrical developed power, PD, and it is equal to tau D, the torque, times omega R, where tau D is the torque developed at the shaft in Newton meters, and omega R is the angular speed of the rotor in radians per second. So if we equate the two equations, equations Q1.1, the electrical power, and equation 1.2, Q1.2, the mechanical power, let me call this M for mechanical, and also let me also change this for M to M for mechanical. So when we equate the two, this is what we get. So I change that to M. Change that to M. Change that to M. Change that to M. Okay, so let's go through that one again. So we are equating the two equations. Mechanical power is equal to electrical power. So tau M omega R is equal to 2ZNP phi divided by C times IA. We are looking for the torque, mechanical torque. So make that one the subject of the formula. So tau M is equal to 2ZNP phi divided by omega R times C times IA. Now, in this equation, most of the quantities are constants. So let's combine all the constants into a proportionality constant. So 2 and 2 cancel out, so that will go. Then we have ZP phi divided by pi times C. We have changed omega R into 2 pi N. Maybe we could have said NR. So this is a constant. The flux can change if we want to change the speed. Therefore, we can say the torque is a constant of proportionality. Let's call it K tau times phi times IA. Now, equation Q1.3 shows us on what factors the torque depends. You can see that the torque is directly proportional to the flux, and it is also directly proportional to the armature current. So that now is the torque developed in the motor. So we can now say we can say tau m in fact, let's now just say tau d, which is equal to tau m is equal to k tau times phi times Ia. So the torque developed at the armature is equal to the torque at the shaft, if we assume losses are there or are negligible, is equal to k tau, a constant of proportionality, times phi, useful flux per pole, times Ia, the armature current. So from this equation, we see that the torque developed is directly proportional to the flux, and it is also directly proportional to the armature current. So in a DC motor, when you increase the flux, you also increase the torque. When you increase the armature current, you also increase the torque, which makes sense because you are increasing the power. Now K is a constant of proportionality, and K, I'm calling it K tau, is equal to Z times P divided by pi times C. And we know what those quantities mean. So the last part is now to find the torque in Newton meters. So let's just substitute what we have in that equation. So when we substitute the quantities in that equation, Z times P times phi times pi divided by pi times C times Ia will give us approximately 400 Newton meters. That is 398.7786. We can approximate this to 400 Newton meters. Okay, that was the first one. The key is to understand the equivalent circuit diagram and to see how to use it, and also to remember the equations. Let's look at exercise 2. In exercise 2, we have another simple exercise. A motor runs at 900 RPM off a 460 volt supply. So this motor is connected to a 460 volt supply, and it is running at 900 revolutions per minute. Calculate the approximate speed when the motor is connected across a 200 volt supply. Now, the supply has been changed from 460 volts to 200 volts. Now, we are not told how the motor is connected, but we are also told that assume the new flux to be 0.7 of the original flux. So when we change the voltage supply, the flux also changed. Because the voltage supply became smaller, the flux also became smaller. So maybe this was a shunt motor. So we want the new speed now. We have changed the flux. If it was a separately excited motor, once again, the flux has changed because the voltage supply has changed. Most likely, it was a shunt excited motor. From exercise 1, we came up with the equation of the speed. This is the one. N in the revolutions per second is equal to EC times C divided by 2 times Z times P times phi. So since we are given speed in RPM, let's maintain our RPM. So we'll change that to We don't need to change anything anyway, but we can, to change this to capital N, we simply multiply by 60. But well, it's not necessary because we know that the rest will be constants. The only variable here is the voltage and the flux. So 60 will be part of the proportionality constant. So we can even do this just to make sure that there are no confusions. Capital N, multiply this by 60. So let's start with 60 here. 60. Okay. And we can write this as EC divided by K. The rest is a constant. 60 times C divided by 2 times Z times P. So it doesn't matter how we write our constant, we can write it in the numerator or in the denominator, we get the same. So in this case, I decided to write it in the denominator. Now, the first case was that the speed was 900 RPM. So let's call it N1. The supply voltage Vs was 460 volts. So let's call the counter EMF corresponding to this voltage as EC1. So in our equation, we have EC1 divided by a constant, which is 2ZP divided by 60 times C, then times the flux, because the flux is changing, so that one is not a constant. So let's call it phi1, corresponding to the first voltage. There was 1 mark for that. Case 2, N2 is equal to, oh, here we don't know the speed, so this is a small error. We don't know the speed. We should have said N2 is equal to a question mark. So let me just correct that small error. Okay, with that small correction, let's go through it again. So for case 2, N2 is not known, so I'll put a question mark there. And Vs has now changed to 200 volts. So going back to our speed equation, we can say N2 is equal to, let's say the counter EMF is now EC2 divided by K, the constant is still the same, and the flux has changed, so let's call it phi2. So the first one is equation 1, the second one is equation 2a. But now we are told that the flux has changed to 0.7 or 70% of the original flux. Therefore, we can say phi2 is equal to 0.7 phi1. Now, in equation 2a, where there is phi2, we can now use 0.7 phi1. So this now gives us N2 is equal to EC2 divided by K times 0.7 phi1. And let's call this equation 2b. Now we've got two equations in two unknowns. Okay, so from equation 1, let's make K times phi1 the subject of the formula. So for this equation, so K times phi1 is equal to EC1 over N1. Now in equation 2b, we've got K times phi1. So where there's K times phi1, we are now going to use EC1 divided by N1. So this will give us N2 is equal to EC2 divided by 0.7 times EC1 over N1. And then we can rearrange our equation. So N2 is EC2 times N1 divided by 0.7 EC1. Now, This is where the trick is. EC2 is proportional to Vs is equal to 200 volt. Maybe we should have called it Vs2. EC1 is proportional to Vs is equal to 460 volts, or maybe we should have called it Vs1. So when we substitute those two in the equation, and we also know the speed N1, which is 900 RPM. So this now gives us a speed of 559 RPM. So by changing the voltage, hence changing the flux, or in other words, by changing the voltage, making it smaller, we have actually made the speed smaller. Now, the change in the flux is not big enough to cause a big rise in the speed. So this gives us one method of speed control, which is voltage speed control for a DC motor. By changing the voltage, we can change the speed, as we can see from this equation. N is equal to 60 times EC times C divided by 2 times H times P times 5. If we keep C, of course C is constant, 60 is constant, 2 is constant, Z is constant, P is constant. If we keep phi constant, or we change it by a small amount, we see that the speed is directly proportional to the counter EMF. But the counter EMF is equal to the supply voltage minus IARA. Now, IARA is a linear, gives us a linear change. But what is important is to notice that the speed is actually directly proportional to the supply voltage. This is what we can see from our result. So this brings the first part of DC motors to an end. Thank you very much.